us discuss about the atomic spectrum. So whenever a gas or vapor it undergoes in a low pressure, it undergoes the electronic jump from one orbit to another orbit, and what we see that there is a release of certain radiation with particular wavelength and frequency, and this wavelength and frequency radiation, they form a kind of spectrums, which is you can say a particular color lines with very specific wavelength and frequency. We call them as spectrum. In case of atoms, we see that every element, every atom of every element has got a very particular type of spectrum, and when we have the spectrum kind of put together in certain, suppose in a particular order of the frequency or in a particular order of the wavelength, we see that there is a set for each and every transition. There is a set of lines that is a very signature of the particular element, and those we call it as the spectral series. So spectral series are the series of, or the set of the spectrums, or the set of the spectral line that we see as a signature spectrum for various elements, right? So now first talking about the atomic spectra, as we have already seen that according to Bohr, that suppose if electron is jumping from a higher energy level to a lower energy level, then it can jump by releasing certain amount of energy in the form of radiation, which has a particular frequency as well as which has a particular wavelength. And just by seeing such spectrum or releasing such wavelength and such frequency, we can guess from which level to which level the energy has been shifted and how the electrons have jumped from which orbit to which orbit. So this we have calculated when we have calculated the frequency and calculated the wavelength, and what we have seen that the wave number, or 1 by reciprocal of the wavelength, is given by this particular formula. Now suppose we are talking about the hydrogen, we are focusing about the hydrogen, where Z is equal to 1, then m e power 4 by 8 h cube epsilon naught into c. This becomes constant, and n1 squared minus n2 squared. This can be changed as the electron travels from various orbits. This constant, which we call it as Rydberg constant, which is equal to m e power 4 h cube 8 epsilon naught into c, and this value of this is 1.097 into 10 power 7 per meter. So this is what is called the Rydberg constant. Now when we just try to calculate the wavelength, here we just need to know from which level to which level the electron have jumped, or just by looking at this wavelength we can find out what level to what level it has jumped. Now when we see that if there are, suppose this is n equal to 1 and there are many different levels, n equal to 2, n equal to 3, n equal to 4, n equal to 5, like that there are various levels. Now from any of such level, electron can jump to the first level. So there are many possibilities for electron to jump from any of the higher level to the first level. So whenever such kind of transition happens, that in a particular level, be it n1 or n2 or n3, electrons from various other levels, when they jump towards a particular level, we get to see a set of frequencies in transition to a particular level, and that set of frequencies of radiation when we put together, we call it as a spectral series. So based on that, hydrogen spectrum has got various spectral series. Now coming to the first one is Lyman. The Lyman series of the hydrogen atom is whenever there is a transition from any higher orbit to n1 equal to 1. So here the first where the electron is jumping, where all the electrons from any other orbit, whenever they jump to the first n equal to 1 orbit, we call all of them as Lyman series. So this is a very nice picture that we have told about Lyman series, where n5 to n1, n4 to n1, n3 to n1, n2 to n1. Here all the electrons from various orbit have jumped to n equal to 1. So this is what we have called the Lyman series, which is jumping to n equal to 1 and n1 equal to 1. So n2 can be anything. Here n2 is the upper level from where it is jumping. n2 can be either 2 or 3 or 4 or 5 or any other level, but n1 has to be the first level. So from any other higher level, when electron jump to the first level, whatever set of the series that we get, we call it as the Lyman series. So this set we call it as Lyman. When from any higher level things electron jumps to the second level, so it can be from 6, from 5, from 4, from 3. So everything that jumps from higher level to n equal to 2, this set we call it as Balmer series. So like that, when from any higher level electrons jump from the first level, we call it Lyman series. From any higher level, when they jump to the second level, we call it Balmer series. So next we have Balmer series, where n1 has to be 2 and here n2 can be 2, 3 and so on. Here n2 will be 3, 4 and so on, any higher level. Next comes Paston, then bracket, then comes Fund. So here n1 is equal to 3, here n1 is equal to 4, here n1 is equal to 5. So when everything comes down to n3, we call it as Paston series. When it is 4, it is bracket. When electrons all transition from any higher orbit, it is boils down to n1 is 5. We call it as Fund series. So like that, we have various series, various spectral series of hydrogen atom, where from any higher level the hydrogens or any higher level the electrons jump to the lower level, and thereby releasing a particular wavelength or a particular frequency radiation, which put together we call it as a spectral series. Now in the Lyman series, the radiations are generally in UV region, so we cannot see it, but all the Balmer lines are in visible region. So for hydrogen, this Balmer series is visible, so we can see it. So just look at this Balmer series of hydrogen spectrum, where you see the alpha line, beta line, gamma line and delta line. So in Balmer series, where from n2 equal to 3 to 2, when the electron is transiting from 3 to 2, we call it as alpha line. From 4 to 2, we call it as beta. From 5 to 2, call it is gamma, and higher delta, and so on. So you see that as the electrons are jumping from higher level to here, the what is happening, the frequency is actually reducing, whereas the wavelength is here, sorry, not the frequency, the wavelength is actually reducing. So the first line in the Balmer series, we call it hydrogen alpha. This first line is the line that it is just exactly higher level to the this lower level. So from n3 to n2, this is the first line in the Balmer series. N4 to N2 second line, N5 to N2 third line, and then so on. So as we see that the first line, which is hydrogen alpha line, it has got 656.3 nanometer wavelength. This is a red line. So this is a red line. The second line is bluish green line. The third line is blue line, and the fourth line is a violet line. So since these lines are visible in visible range, so we can see the Balmer spectrum of the hydrogen atom, and like that there are various series of the spectrum that we can calculate for any atom. So every atom has got such very significant and signature spectral lines, which is kind of decide what type of elements are there. So looking at a spectrum, we can kind of analyze what elements are present in that particular way, and therefore the atomic spectra and the whole study of the spectrum, atomic spectrum and the spectral series remains very important.
If you like the video, then press the like button, subscribe to the channel and press the bell icon.